Homework number 2 is due now. I'll have the key posted this afternoon. I've got the exam written. The first question asks about the... so we'll talk more about the exam at the end. Any quick questions on homework number 2? I'll have the key posted as soon as I get back to my office. I thought these were pretty straightforward. Yeah?
Did we have to analytically evaluate the Nano constant? Or did we
No. No. Yeah. I mean, just to, yeah.
Well, the exam consists of also recognizing Taylor expansions, because in order to solve one of our homework problems, we need to recognize Taylor expansion. It's not something that's necessarily quickly intuitive for a lot of people.
Yeah, that was a harder question. Yeah. I don't know yet. You won't have to derive one from, yeah, you won't have to derive one on the test, that's for sure. You may have to use one. Okay. So then homework number 3, I know this is kind of a crunch, is going to be due tomorrow at 1 o'clock outside my office. And I'll have a key posted then at the same time. I'll have an office hour tomorrow from 1 to 3. And then the exam will be on Friday. And then I'm going to send out a doodle poll, like I said, about teaching style, just because this is my first time through, just to get some feedback. I'll try to keep it like less than 10 questions, just to help me make the next 1/3 of the class better. Yeah.
It says it's due tomorrow at noon at 1.
Yeah, that's a typo. It's 1. Tomorrow, outside at 1. Yeah.
How much of the orbital shapes do we have?
We'll talk about the exam at the end, okay? Other questions that are not about the exam? Okay, so last time we talked about molecular orbitals, and we talked about valence bond theory. And we mentioned that we can come up with unique wave functions for those new hybrid orbitals, right? And so the one that we derived, and well, we didn't derive, but the one that we discussed and showed that they were orthogonal with each other and normal across, for example, mu A or psi A and psi B. We showed that those would be orthogonal, and we showed that psi A is 1, right? But what we did last time was for an sp3 system, right? And here are the system for an sp2 hybrid orbital. So for something like ethylene, right? And so similarly, these exist for just SPs, right? We could look this up as well. Does it make sense that there's only 3 wave functions here, right? Whereas when we talked about sp3 system, we had four different wave functions when we talked about this in last class, right? Psi A, B, C, and D, because there are 4 hybrid orbitals. Okay? Whereas for this, in an sp2 system, there's only 3 hybrid orbitals. 1, 2, 3. Okay? And these describe the shape of those, right? Okay. So other things you need to remember about sp, sp2, and sp3, the number of hybrid orbitals, the number of groups bonded to carbon, right? So if we have an sp3 system, it's a CH4, 1, 2, 3, 4, so on down the line. So if we had an sp2 system like this, it's only 2 things bonded to the carbon. One is the other carbon, and one is the hydrogen. How many sigma bonds and how many pi bonds in this system? Right? That should be second nature, right? We've got one sigma bond and 2 pi bonds. Similarly with sp2, we'd have 1 sigma and 1 pi. Okay? Okay, so that's still kind of review. So that was kind of valence bond theory, right? And now we're going to talk about a slightly different way of looking at covalent bonds, molecular orbital theory. And these, when these are taught, I kind of divided it into 2 different sections, kind of because that's how it was done last year. You can really think about these in tandem. Today we're going to draw more of these molecular orbital diagrams. And so don't get entirely hung up on, like compare and contrast valence bond theory versus molecular orbital theory, because they're both an approach, and neither one is exceptional, especially always true. Okay, so let's go back then to our, not this, something like this. So when we were talking about a very simple system where we have hydrogen A and hydrogen B, okay, and we said that these can combine, and that they both have 1s orbitals. Okay, and that this bonding sigma bond will occupy both of those electrons, right? And that this sigma antibonding will have 0 electrons. What's the energy of this in electron volts? Negative 13.6, right? And people have shown experimentally that the difference is roughly 11, negative 11, right? Which makes sense, that the difference between these two is going to be less than the energy of either one of them, okay? Because this forms spontaneously, right? This is moving to a lower energy because you're getting that spin flip. Okay, so how do you do it? You can take pure hydrogen and shine light through it and see where that absorbs and see where you get a transition from that to that. Okay, you're putting energy into the system in the form of light and getting an absorption of that photon. Yeah?
The absorption causes a spin flip?
No, not a spin flip, but a promotion to a, so it would look like that. Right? So it's still a singlet state. Triplet would be if it flipped. Yeah. Okay. So let's talk a little bit more about the shape of these orbitals, right? We talked about that this would be the shape of this anti-bonding orbital, or excuse me, bonding orbital. And that our anti-bonding would look kind of something like that, right? With a node here. Okay, node. And that this is the anti-bonding. So what molecular orbital theory says is that the wave function for this system is, again, we have this awaiting factor and that this is actually can be plus or minus. And this is our destructive or destructive interference. Okay? So if we are if these are both completely, if we have all A and all B, that's when we're at our node, and these completely cancel out. Okay? So remember how this is our plus and minus, and we could have just as easily inverted this, right? How we called A and B. So this is the kind of molecular orbital theory approach. Okay, and remember how it looked last time? Where we said it was so this was with our valence bond theory. This is what we showed last time for a covalent system. So here, it's essentially as if these individual electrons no longer exist. That's what these 1 and 2 were considered, right? Electron 1 and electron 2. In molecular orbital theory, we're essentially considering this to be these individual electrons to become one molecular orbital that's distributed over the entire molecule. Okay. So if we were to normalize this, what do I mean when we normalize it? Square it, right? If we normalized our molecular orbital, you would get right, this is this, squared. Okay. I'm going to skip this. I'll post this derivation all the way, but we can assume, what can we assume here in terms of our C's, at least for hydrogen? That these weighting factors, they're equal. Yeah, they're going to be equal to each other. And so that's the only key assumption that you have to know to go on and solve this. For C is 1 over square root of 2. Where S equals okay. So what this can, okay, so this is our weighting factor. And then, I'm going to hop over here. So this S then changes as a function of how close these two objects are. Okay, so when they're completely on top of each other, there's no longer there's complete overlap, right? You no longer have two systems. Okay, and then when they're infinitely far apart, you have less and less and less and less overlap. Okay. So this is the most simple way of understanding how the molecular orbitals would combine in a 1s system. Okay.
Professor?
Yeah.
Is that supposed to be 2 times 1 plus or minus?
You're right. Thank you. Same thing. Okay. So what if we moved into then a slightly more complicated system than helium? What's our next most complicated system? What's in between? Helium. Yeah. What did I say? Did I say helium? Oh, okay. So, actually, so what does this look like? 1 up, down. Okay. So these are both their 1s orbitals. Okay, so what would we do here? Fill this, right? Sorry, that's anti-bonding. And then we have to fill this. Do you think that's stable or non-stable? Right? This doesn't exist. But what you can get is,
How do you know if it's stable?
because you have the same number of anti-bonding,
Oh, okay.
you have 2 anti-bonding electrons, right? And 2 bonding electrons, okay? This is stable, because now you have more bonding than anti-bonding electrons. You can actually even calculate, or measure, not calculate, measure the bond length of He2+. Yeah.
So basically, anti-bonding, is it like a repulsion?
Yeah, it is. Yes, exactly. It's a lack of the orbitals overlapping, right? What we're getting here in a bonding orbital is overlapping of the individual atomic orbitals into a molecular orbital. And here it's destructive interference or a lack of overlap. Yeah.
Sorry, I just missed where you said that other electron goes.
Oh no, so let's just say we ionized it. Let's say somehow we ionized our helium gas. Yeah, with energy. Yeah. Yeah.
Why doesn't it form like why doesn't it instead form like an SP, like an sp2 hybridized orbital?
Because helium doesn't have a p orbital, right? Yet. Yeah. Yeah.
So anytime the anti-bonding electrons are equal to the number of bonding electrons, it's basically unstable.
That's right. And that is what is known as the bond order. Okay? Hold on. Let me finish this. The bond order is the number of bonding electrons minus the number of anti-bonding over 2. So in this situation, it's 2 minus 1 is 1 over 2 is 1/2, a bonding order of 1/2. Okay? When we had regular H2, which doesn't exist, our bonding order was 0, and therefore there is no bond. Yeah.
Does any positive bonding order mean that compound can exist?
Yeah, any is always such a difficult word. It generally means that it's a positive. Yeah, it generally means it exists. And not only that, it generally indicates, is it a single bond, a double bond, or a triple bond? So if you had when we do nitrogen, you'll see that nitrogen's bond order is 3, and that has a triple bond. Yeah.
Have they calculated like the energy associated with anti-bonding and bonding orbitals?
Yes.
And like how much
Not calculated, measured.
measured? How much like is like the bonding versus the anti-bonding?
Say that again.
How much energy is in the bonding versus the anti-bonding?
It's unique to each molecule, right? But there obviously, it takes more energy to get something into the anti-bonding orbital.
Yeah.
Yeah. Yeah.
So you said that like a bond order of bond is a small bond, so what's a bond order?
An ion,
Okay.
right? So yeah, it implies an ion, yeah.
So when you have O2, usually like O2 negative, that's a bond order of 1/2, so that tells you that the half is like...
That there's an ion, an unpaired electron on that system.
Does it tell you, like, is it a positive or a negative ion? Like, if it has an extra electron, or did it lose an extra electron?
That's what the charge says. So here it's a positive, so that means you lost an electron, right? So so that's I think that's on your homework question, right? You've got O2 minus and O2 plus. So in that situation, you would draw out your regular O2, which we'll do, and then you would just add or subtract an electron based on that charge, right? So similarly, like does it make sense that this is also 1/2 H2 plus, right? If this was, this is H2 plus, right? Only one sad electron, right? And here, so our bond order is 1 minus 0 over 2 is still a bond order of 1/2. Okay? Does it make sense that this bond length is shorter? Right? That makes sense, right? If we had H2 versus H2 plus, that's clearly going to be more stable, right? More stable. More contraction. More electrostatic interactions. Shorter bond length. Okay. Okay, so now let's move on to something more complex, to like nitrogen. Okay, so what's nitrogen has? It's 1s2, 2s2, 2p3, right? We can, we'll do it the first time. We can do 1s2, 2s2, 2p3, right? So this is px, py, pz. And they each have one electron. Okay, same thing over here with nitrogen, number B. Px, py, pz. This nomenclature is impossible to keep straight, and you kind of just have to think of x, y, and z as being interchangeable because your book does it one way, another book does it a different way. I think when I discussed it with you last time in class that we said to think of the z as being the z-axis as being in between the atoms. But just be aware, when you go back and read the book, they don't always maintain that nomenclature, and especially when you start to look at other websites, they definitely don't maintain that nomenclature. So, but these are, what's the word for these three orbitals? They're degenerate, right? So it doesn't matter why we describe that. Oh. Okay, nitrogen B. So this is going to do the same thing, right? We're going to get a sigma bond here. Okay. Your book has this drawn out much nicely. Especially it becomes important, the energy, increasing positive energy This is how these are written, right? So these are the most strongly retained electrons, the 1s electrons, right? These are the electrons that are loosest, that can participate in bonding, increasing energy. So how you draw this does start to become important. So see how here I didn't necessarily give myself enough room, but my sigma 2s is lower is definitely going to be lower than those two original 2s orbitals.
Professor, you said lower?
Yeah,
Or lower than the 2s?
lower than the 2s. Yeah, not lower than this.
Professor?
Yeah.
In bigger molecules, do you see the 1s orbitals still bonding like that? Like I feel, in my head, I feel like they wouldn't be as close together. They wouldn't want to bond as much.
They're kind of shielded. You are right in that these are, your valence electrons are what are participating in the bonding. So that's why this, when you look at the bond order, this cancels out.
Oh,
So frankly, you could have completely skipped writing those out because they're not the valence electrons.
I see.
Yeah. Okay. So that's our 2s. Now what can happen here with these p orbitals? And here you kind of have to think geometrically. If you've got an x, a y, and a z, p orbitals, yeah.
Is that when there's no anti-bonding for the...
It's coming, yeah.
So PX is usually the same kind of energy or a little bit higher than the answer at 2s. So like they're a little bit off. So like you have two x, y, and z. X, y, and z.
Yeah, you're going in the right way. What I'm trying to get at is that you have the right symmetry in order to get one sigma bond and two pi bonds, right? Because the only sigma bond that you can get that's symmetrical around this axis is between, whether you want to call it x, y, or z, it doesn't matter, but you only have room to make that one sigma bond, right? Okay. So let's draw our other 2s antibonding. And now, you know what, let's just jump right to the one that they drew because it's going to be much more accurate. Okay. Now, to make it even more damn confusing, G and U is just another nomenclature for bonding and antibonding. Okay, so U is antibonding. Okay. So here's our 2s bond, sigma bonding, sigma antibonding. This is our pi bonds from two of our p's, right? Either the px or the py. Okay? Yeah.
Why is pi u lower than pi g?
It's a function of the molecule.
So like it stands for like that like nomenclature that stands for German letters.
Gerund, yeah. This sigma bond changes in energy relative to those two pi bonds depending on the species electronegativity.
So like that part implies that the antibonding orbital is still before the bonding orbital. So it's,
Yes. So, yes.
Does it because of the numbers of protons? Or?
The number of protons. Yeah, so as these, look how all of the sigma, even the one at the 2s sigma bonds, I am going to ruin my computer, also become lower, right? These sigma bonds drop in energy as you have a more electronegative element. And as they become, as there are more and more protons. How come? Because the protons are holding on to those electrons even stronger. So the energy, it becomes a more negative value, right? So, but between nitrogen and oxygen is when you get this flip, this inversion. Yeah.
How come the pi bonds don't decrease as much?
Because that's a great question. Why don't the pi bonds, so these he's saying, look how the pi bonds here are relatively steady, right? So think about how the pi bonds are, right? They're more up here, whereas our sigma bond is much more localized between the two nuclei. So as the number of protons go up here, the degree to which these electrons are withheld between the two protons is much more strongly affected than the pi bonds that are out here, right?
So doesn't that destabilize the compound?
To have fewer compounds, or to have fewer electrons.
Like if the electrons aren't sitting in an antibonding group, doesn't that destabilize it?
Yes, exactly. The more you have in a antibonding orbital, the less stable it's going to be. Yeah.
I think where I'm confused at least is why is the antibonding of the pi orbital lower than the bonding to the pi orbital?
Why is the antibonding?
One pi u is below one pi g. Well, it looks like
Here?
Oh, just above that. So that's pi u and then pi g above that.
Yeah, so like it's not since it's there's the like just the question is since it's in pi u like that it might be just basic stuff, but
Why is antibonding lower energy?
It's not.
I was
Yeah.
asking about the thing before. It was 'cause
This should be the antibonding.
yeah.
Is the diagram wrong?
But it was the same. It was the same on the pi diagram. It said that pi u was below. Pi was lower energy than pi g.
So here G is lower than U. Here G is lower than U. But why is that not? That doesn't when you do this on your homework and on your test, don't use that G and U nomenclature. Use the star and non-star. And so if we were doing it like I was drawing over here, this would be pi 2p antibonding 1 sigma. Oh wait, I'm sorry. So which one did I say we're doing? We're doing nitrogen. Yes, and so this, and then here we have a sigma. And then we have another. Okay.
Top two are antibonding.
Top two are antibonding. And that's what this is showing here as well, right? For nitrogen, those two, then the 1s, then the, except for this. Okay, so is that a typo? Sure looks like a typo to me. Yeah.
In the original column we have going
Yeah.
here, you're saying that we need to kind of copy and paste what you just wrote here in between the sigma 2s and the sigma 2s antibonding? Because it looks like you're putting the 2 pi orbitals in between the sigma bonding and antibonding.
This one, okay, yeah, so this can form a sigma bond, but then these can also form a sigma and 2 pi's, right? The 2s orbitals are going to form a sigma bond, but also this is what would go in between. Yeah, exactly. This goes.
So that goes underneath the sigma 2s antibonding that you have there?
No, this would start then right here.
So we have another sigma 2s antibonding on top of all of that. So we have 2 sigma 2s antibonding.
That would be a 2p.
Yeah, that would be the 2p. Yeah.
Okay, thank you.
Again, the reason there's 1 of this and 2 of this is because of the symmetry between your p orbitals. Yeah?
Aren't the pi bond be more stable than the sigma bond? Isn't the little bond over the sigma bond?
So you're saying for here, why would the sigma be? Because when you have, in situations like this, you just don't have as many electrons, right? So the sigma bond in carbon doesn't have any electrons, right? It's hard to hold a bond together if there's no electrons there, right? Whereas here, your pi bonds, he's saying, look, you told us that pi bonds have less electron density between the nucleus. So how can it possibly be more stable? Well, it can be if there's electrons in it and there's no electrons in.
So then
This-
why does it preferably fill that pi first rather than filling it first?
So why is this pi bond at a lower energy level?
Why are electrons going into that pi bond after, like, before they're going into the sigma bond?
Man.
Like how big the electron cloud is. If something's less electronegative, it might be able to be more delocalized and then more easily polarized when they're like coming off these perpendiculars.
Yeah, that's a good question, is why you would punch it in here. And maybe also because of the fact that you also have already a sigma bond here from the lower energy level. And therefore, as carbon has fewer protons, its ability to retain an additional sigma bond within that space is lower. Not really, I don't know that I believe that, because you can easily form a double or a triple bond, which are pi's. Let me think about that. I don't feel like I have a...
It's the idea that it's like, it looks almost arbitrary that for oxygen and fluorine, we're splitting sigma below pi, but then every other atom for that same row for pi is underneath the sigma.
This makes sense to me, right? That
Yeah.
that these drop in energy as you become more electronegative. But you're saying this here, why is that? Why is it ever over there? Why would that not fill first? Man, I don't have a good answer. Yeah.
So what happens between nitrogen and oxygen?
What happens between nitrogen and oxygen? It's this where you're becoming radically more electronegative, right? Was your question again, why are we seeing this?
No, I mean the bond between nitrogen and oxygen. If we bond it together, like would it be?
Yeah, we're going to do HF because we're going to try to do HF. Boy, that's why I eliminated those two from the homework questions. I said you don't have to do 5C and 5D where they're heteronuclear. But you have to consider the electronegativity differences as well. Yeah.
So I have 2 questions.
Yep.
So could it possibly have to do with the fact that electrons also repel each other, so they don't want to all stack into the sigma bonds, so they occupy some pi?
Yeah, that could be it too. Did you catch that? Catch her point is that there's repulsion between the electrons, and so therefore to create another sigma bond would kind of be disfavored because you're putting another sigma bond in between. Whereas putting those next electrons in a pi orbital, you're increasing the space between the electrons.
But then why would it be for oxygen and fluorine rather than work the other way?
Well, then because it's easier to create more sigma bonds because you have more protons between your two nuclei. Yeah.
A question about the geometry of bonding here. I noticed in this case of nitrogen and nitrogen, for both the 1s and 2s orbitals, we have an even balance, meaning a zero bond order between bonding and
Yep.
antibonding. But here in the 2p energy level, we just have 3 bonding orbitals. So is that why we see the sigma bonds from the 1 and 2s levels don't actually connect? They're just sort of there and accounted for?
Yeah, so I mean, if we were to calculate the bond order, if we wrote it just like this, it would be 6 minus 0 over 2, which is 3. Or if we considered all of this, it would be 10 minus 4, which is 6, right? So here the bond order, well, the bond order for all of these, for nitrogen, is 10 minus 4 over 2, which is 3. So there's 6 bonding electrons there, plus 7, 8, 9, 10, minus these 4 is 3, right? Yeah.
So I guess I think is why it's saying that there's a pi bonding and anti-bonding in the one space.
Pi bonding and anti-bonding.
Where's the one pi coming from?
Oh, this? Okay, so you're saying why isn't that like a 2 pi? In their nomenclature, it's probably because that's the first pi orbital. But I would use this notation, pi 2p. Yeah.
I want to clarify for so between, you see these interactions between the 2s and the 2p orbital.
Yep.
And then not the 1s. Sure. So I know this is one, but it's just nomenclature is what you're saying.
Say the question again.
So the interaction between where you see the pi bond below the 2s, that's referring to the 2p, what make the 2p.
That's right. These are all from p orbitals, right? The original p orbitals on these diatomics. Okay. Let's talk about. I was going to try to get through hydrogen and HF. Yeah.
Sorry, but my question is, why don't we just have 3 pi bonds when we're doing, rather than having a single bond and 2 p?
Why?
Like pi x, pi y, and pi z.
Because the symmetry between those two, right? You only have one p orbital that could potentially overlap. Right? And then you have one going in and out of the board. Right? This is the only one that can make a sigma bond because of the symmetry between those orbitals. Okay? So the midterm will be based on the lectures and the homework. Again, I've never written an undergraduate midterm, so I think it's fair. I don't know. I finished it in an hour. So I also wrote it. Again, like I said, this will be weighted, and so we'll see how it goes. It'll be based on the lectures and the homework. Bring only a calculator. There's no cheat sheet. If you need an equation, I'll give it to you. All those derivatives of Coulomb's law that we looked at, the van der Waals laws you'll have. Why don't we do questions after I finish? You should have basic equations memorized, like the areas and volumes of circles, squares, rectangles, spheres. You should know the Pythagorean theorem, the quadratic equation, like those kind of nuts and bolts you should have down. Last year, I pulled up the midterm from last year, and it was kind of overkill. I'm inclined to not give you something like this. You would have all the constants. If you needed a constant, you would have it. If you needed these elemental charges, you would have that. I'm inclined to not just overkill. I'm inclined to just say, for this problem, here is the expression. You should be very comfortable. There's definitely going to be something about these will also, the radial and angular wave functions will be given as a supplement as the test, so you'll need that. you'll need a periodic table, and I'll also give you that. That's not a shower curtain. So radial and angular wave functions. So I just kind of went through in my mind what we had talked about: surface area to volume ratio, spherical cluster approximation, functional groups, periodic trends, including electronegativity, the ability to write electron configuration and quantum numbers, Lewis dot structures. So that was like our first little bit. Using Coulomb's law and using it to calculate force and energy for an ionic situation, an ion dipole, dipole, dipole. Van der Waals, we'll probably not have anything about Van der Waals. Be able to understand how these forces relate to each other in terms of strength and bond length. Be able to discuss potential energy wells. Be able to discuss and calculate lattice energy Born-Haber cycles. Okay? Hold on. Atomic orbitals, so be able to describe, use the wave function, the radial and angular wave functions, be able to normalize and show that two wave functions are orthogonal, be able to predict the orbital shapes and nodes from a set of quantum numbers, and yeah, orbital nodes, that's redundant. And then on molecular orbitals, how far did we get today? Predict the nature and shape of hybrid orbitals, so SP, D, and then also SP2, SP3, SP. Construct a simple molecular orbital diagram, so it'll be one of these. It'll be one of these that we looked at, a diatomic, if it's on there. And we didn't get to highest occupied and lowest unoccupied, and we didn't get to that. But do be able to calculate bond order. Okay, questions? Yeah.
So for the video lectures that you post on YouTube, I tried accessing it, but there was only...
Email the TA.
Okay.
They're all up, yeah.
Is the caliber of the work similar to what we will see on Friday?
Yep. Yep.
By fancy equations, do you basically mean anything we derived in class?
All of those, yeah, ion dipoles, yeah, I think even if I ask you for, I'll probably even tell you this, like Coulomb's law. I'll probably even have Coulomb's law written down. Yeah. Up through a TI 86.
No Taylor series expansion, Taylor series approximation for it?
No, there will be no Taylor expansions. Yeah. Any other questions? Okay, good luck.